Now with that in mind, that coming break, I wanted to finish up some discussion that we started last time. And have an exercise as well that I hope will help equip you for offering me some specifications as part of your ID2 and ID3. Specifications are required in this course for elements of deliverables, and I want to see them, and this lecture should give you a clear understanding of what I'm looking for in those specifications, because we talk about elements of it in some detail. Okay, so you'll recall that in our previous lecture, I argued that modularity is a key feature we look for in making manageable large complex systems. We look for opportunities to carve it up into pieces that can work together to accomplish the tasks, right? Where each of those pieces is well defined. And I argued here before that to take effective advantage of such modularity, we need to use abstraction on this process of hiding details. We build up these pieces, modular components that handle equally well a wide variety of circumstances. And we allow many specific cases to be captured by a certain abstraction, captured in a module of whatever sort, class, function, a method, whatnot. And through that, we achieve generality in these pieces. And I argued from this floor on Tuesday, 2 days ago, that there were two types of ways in which we abstract away from detail. The first of them was the one that I would surmise is most familiar to you from other classes. It's the one that immediately comes to mind if you think about an abstraction sort of handling many particular cases, and that is we parameterize our abstractions to take different information to adapt them to different circumstances. So we use parameters, be they type parameters or parameters that take in values. And you'll recall some examples I showed, but basically we carve off, an add vector routine where we pass the two vectors together. That's just V1 and V2, right? Or instead of having a count male, count number of people in the population, and a male count number of the female, we have some count population and pass it sex, right? Or we have type parameterization that says this is a linked list of doubles, or this is a linked list of hash tables, or this is a linked list of heaps or whatever. So abstraction by parameterization, we have these parameters that give this abstraction generality. We can pass different parameters and have it do different specific things, but with that same value, right? And I actually gave reference last time to ways in which that also intersects with subtype. So we might have a module, maybe it's a function, which takes in, so we might have foo. That isn't so good. In search of working markers. So we might have a function foo here, which takes in a reference to some object of that implements some interface I. And we can operate on I by calling methods on it, etc. And this also has a requisite flexibility because we can pass in an instance of any subtype of this interface I, right? Is that familiar to you from object-oriented languages? With parameters, with subtyping, right? You have a routine that takes a fruit, you could pass in a banana because it is a fruit, right? It satisfies all the properties of fruitness, which I will not list. Or you could pass in an instance of an orange or an apple, the kiwi, indeed a rambutan, or a mangosteen, or a durian, the king of fruits. Rightly designated. So you could pass this in here because they're all subtypes of fruit. It has this generality to operate on individual subtypes. That should be familiar. So in the context of object-oriented languages, abstraction by parameterization has some special kind of structure to be able to pass in things that are subtypes of the parameter. But what I wanted to concentrate on in this lecture, and I also tried to hit really strongly at the end of the last lecture, was this other type of abstraction. It's abstraction by specification. And here, we're not handling many particular cases by having parameters that encode the particulars of the situation, the particular vectors to be added. No, instead what we're doing is providing a specification. And by doing that, we allow the implementation to evolve as long as it adheres to the specification. Do you remember that general idea? As long as the implementation adheres to the specification, anyone who uses this abstraction, their code should still work because they're only counting on the features of the interface. So I won't go into the parameterization more, but I do want to talk about this abstraction over implementation details, abstraction by specification. So what we were trying to deal with is to avoid problems where, like, this abstraction, we change its implementation, we change whether it's sorted with a slow algorithm or a fast algorithm, going from bubble sort to quick sort, and we break code as a result, right? It breaks code that uses this abstraction because it violates a property being counted on by that code. In this case, the ordering of ties are maintained. In abstraction by specification, to deal with that problem, it adheres to this principle of separating interface, the specification, from the implementation, the particular thing that realizes that interface, one particular realization. And the details being hidden here, instead of being details about, the particular data structures on which we wish to apply and add vectors, these two vectors or those two vectors, capturing that through parameterization. Here, the details to be hidden are the differences between implementation. We hide those details by an interface, and we say the person who creates the abstraction, in this case, like sort, they can choose an implementation as long as that adheres to certain properties that are specified in the interface. Okay. As long as the interface still holds, as long as the contract, what interfaces are, contracts. They say, for me to do my job, you have to give me this with these preconditions. And if you do that, I will give you that with these postconditions. And as long as that contract is maintained, we don't have to worry about the details. And I gave the example of FedEx, right? You don't need to know about all the details of FedEx's systems. What you need to know is they adhere to a contract that if you send off a package and you give it to them by 1 p.m., they will get it to Toronto by noon the next day or whatever. They'll adhere to that promise. You don't need to know particular flights they're using, particulars of their IT system, what trucks they're using, when exactly they'll get it to the planes. That's all implementation details. And as a result of you not counting on it, they can change them. Mm-hmm. So there's a lot of benefits here. We can build up. I had a diagram last time over on this side of the room, and you need to be fair. The calculation for what certain nutritional content to do this. Different area. But if we had some piece of code A, from module A, and it calls off to BCD, maybe these call each other, what have you, maybe there's control recursion going on. As long as these things are spec'd out in interfaces, as long as the properties that they observe, the guarantees that they make, their contracts are well defined, we can write A without knowing about those details. In fact, we can write A before B, C, and D are ready, right? And we can also, when we're writing A, use B, C, and D in ways that we're confident will work, that will give us what we want. We can change things. So remember I argued that modularity becomes hellish if every time I change one module, all the rest have to change. Or if it propagates in uncertain ways, right? That are changed to something like this, breaks all the uses of it across the system. That's not an effective way of building complex software. Instead, what we want is the ability to modify things within the limits specified by the specification, and know that with confidence, what other people are counting on for our code is going to be assured. It's guaranteed. Does that make sense? Okay. And then you have some reuse opportunities, right? You could potentially have some piece of code, for example, that calls off to only an instance of some interface. And we don't need to know what implementation of this interface it is, right? We can, as long as it does the right thing, it guarantees the right properties, as we call it, with various of its methods. We can use that without knowing which particular implementation of interface I this comes from the orange, from the apple, from the banana, and indeed, mark my words, from the durian. So here we get some reuse. We have the ability to reuse code long after this code is written, long after this code is available in libraries. New instances, new classes that implement interface I can be created. Classes that didn't exist when this code was written, this code in foo. And we can be confident that this code in foo will work with them because they guarantee certain properties. Does that make sense? Are people tracking? Okay, no. So sounds great. We're going to be talking about how you achieve specifications like that. Okay, so it simplifies our life. It lessens the amount of work. And by choosing the right abstraction carefully, we can buffer ourselves against anticipated change. We can hide the details of things behind abstractions, carve them out into things with specifications, so that those details can adapt over time, can change as needed. We just need to modify the implementation, not the rest of the system. The key question here, at an operational level for you folks, for what I'm expecting to see, and I mean, and subsequently, is properly addressing this challenge of defining the interface. Okay, it's great. You have an interface that defines a contract, a specification, but how do we do that? How do we get that in place? Well, we know you should know how not to do it. I mean, you can't just say the types of the things being passed in for the parameters and the types being returned. That's not going to be enough to tell us about the properties, the behavioral properties we're talking. No, not at all. It's not just the signature, the type signatures. We want some other way of knowing about the behavior. We want a contract that specifies that behavior. And there's actually a whole area of software engineering called design by contract, which focuses on. Okay. So we're looking to build up a contract that's indicated by specification. Now, contracts come in computer science because they're so central to our discipline to allow for graceful evolution, nimble evolution that is localized changes that don't make our life a living hell by causing problems all across the system. We have many types of contracts in software engineering. We have contracts that use types very strongly, but also contracts we're going to be talking about that provide semantics of behavioral guarantees with pre and post conditions. And for classes, we also have invariance and history properties, which we won't be talking about today, but in a later session. And there could be performance contracts, like if you have real-time systems that provide guarantees that a certain task will be finished in a certain amount of time. So for embedded systems, for example, as might be used in engineering, we will often be concerned with the real-time performance of a system. And quality of service contracts that guarantee certain things with latency and the turnaround time, et cetera. So what I argue from this desk and indeed floor last time is that with our specifications, we need to balance two types of we need to provide enough information to make the abstraction, make the thing whose behavior we're describing, because we're creating it, able to be used to clearly deliver functionality that's desirable, people can count on. And to rule out implementations that won't work for those users. But it should be general enough, flexible enough that we can evolve it. We don't want to box ourselves in so we can't have nice performance advantages, like changing a bubble sort to a merge sort. And it should be clear enough for people from a variety of backgrounds to understand, so people can count. So if we can achieve that, we've achieved many benefits. And I'm not going to dwell on these more. I've emphasized these, it specifies guarantees in which we could specify these benefits broadly for users of the abstraction and the creators of the abstraction. By users and creators, I'm talking about like if we're defining C, that we're creating C, we're a creator of C. User of it might be A here or D because they're using C. They call up and expect some services to be provided by C. You see they have these arrows into C because they use it, right? So there are benefits that come from this for those who create C and those who use it. The benefits for those who create it are They can write tests against it, right? Before the implementation is complete. They know what they're guaranteeing to others, and they should be able to write tests for that, right? Now, this is a point where I'm tempted for rhetorical purposes to climb atop a chair. But occupational health and safety regulations prescribe that. So I'll just say you should write tests against your specifications. When you provide specifications for your code, one of the big benefits is it should lead you to think through what goodness would there be that would test this behavior. It practically begs for certain tests. Tests that the post condition is realized, for example, if the preconditions are realized. That certain error use is ruled out. But you also, as the creator of C, person is building up this abstraction to be used. You also know what you can modify in the future, right? You know that you can change it from a bubble sort to a merge sort and get rid of that embarrassing bubble sort, going from n squared time to n log n time, and the number of items in the array being sorted. You know you're free to do that. But you know you're not free to replace it with a quick sort, because that would violate the features that others might be coming. On which they might be coming. Are we following? Okay. Now, users of the abstraction. Almost all. I'll have it. No. Can't think of a single example for this class where I didn't include an example on this slide. So follow the red dot, folks. So the users of the abstraction, like A over here, they get great benefits too, right? Because they can write code against the abstraction we're creating without risk that the world's going to be yanked out from under them because we're going to change C and it's going to break their code. We know the features, the properties of this on which we can count. And we're forewarned because if it's not in the specifications, we should have fair warning that we can't count on it. So we don't have to guess. We don't have to go read the code. If the folks who are creating A have to go read the code to C, why is that a problem? Give me one reason that they have to read the code. Slow. Yes. Slow and painful, right? Maybe it's in a language you don't know too well, right? Maybe this is in Rust, which you're just learning, and this is in C++. What do you mention that? Good language. Maybe this one's in Rust and this one's in Gouda. You want to do this and do because they're working. And it's slow, it's painful, and across a large system, multi-million lines, it could really be a lot of work to go and review this. But what's another reason that even if you could read the code, even if you do, it doesn't provide guarantees for the creators of the users of this abstraction. You're going to see for the people who use it, I'm saying, even if they have access to your code, oh, it's open source, I can go look at it. Why does that not provide guarantees that on which they can count? Yes, Connor with an E.
Because they could change it.
C can be changed.
So
Yeah. It's not enough to provide access to the code because the code can change. Does that ever happen? Enough said. Okay. It also provides benefits for early reviews of the design, right? I mean, the specification for C is just begging to be reviewed in an inspection or in a pull request, a review of a pull request, etc. You could directly derive many assertions from the specification. You can almost read out a lot of assertion from it, much of the time. Preconditions, depending on your philosophy. I spoke with you about this from Seattle. In one of the opening days of the course, you either want to turn them directly into assertions or you turn them into error handling, one or the other. The question is, do you commit to handling violations of them, even though you say, I'm counting on them? Is that your job to do that? If you decide it is, then you handle them as errors. Otherwise, at least you assert them and say, look, whoever's calling this has to fix their code. You can derive conditions for mocking of this, right? If you're writing C and you have an interface that specifies what preconditions C is counting on when it's called, say by A, and what post conditions it guarantees, you can turn that into a mock very easily. Something that maybe C isn't fully written, but you substituted a mock for it. Or maybe you just substituted a mock so you can observe A in isolation without testing C as well. And it tests, are the preconditions met, and it returns something that's legitimate as for the post condition. You can create test cases for C, right? I want to see that. And as we'll talk about and later in the semester, less risk of violating the list-of substitution principle. So look, I know this takes time. I know specifications take time. We're going to unpack what they look like. But often there's really substantial time savings in preventing testing and debugging bottlenecks within your system. Okay, so here we have a routine. The job of this routine in its life is we have a string to be found and a string in which to find it. Sure, find it in is when we look in to find this string being found. And specifically, if we give it a string being found and a string find in, we're going to look for this string in that one. It finds the first index of the string being found. In the title of this string being found within string function. So if I were to give you this, what can you give some ideas of plausible things? You don't know exactly what the implementation is going to be, but can you give some sensible properties that you might reasonably impose on? I'm not saying that they have to be imposed, but some of them might follow, like it's hard to imagine you not imposing them, and others might be sensible things you might want to insist on as you write find first that would still keep it a useful function, but rule out, ill-defined uses of it. So what things can you give me a few things, Tanner? Good. Okay, so this is gonna have some. I love the ideas. So first of all, does it make sense that string being found is a string that's empty, that has no characters in it? Does that make any sense? Not really, right? It's hard to think of that as being well defined. String find in, could this be empty? So if it's empty, I should say, I'm sorry. Yeah, so this is part of what you'll have to spell out here. But clearly you're going to need some more information than this. You're going to need something that specifies how you handle a case where it can't find it in there, right? Because it's not saying that right now.
It's also not saying like, what's the first index, right? So let's start talking about it. So I like Tanner's idea. Like this has to be non-empty. This one is a little bit more debatable, right? Like you could look for foo in the empty string, a string that's empty, and as long as you could signal, I can't find it, right? And so you'd need to handle that case. I'm asking here to sharpen how we specify this. This is a really crude statement as we're seeing. We have to include other information, and specifications require us to think that through. Okay, so possibly you certainly seem to want this to be non-empty. This one, you could require it to be non-empty, but that would kind of rule out some uses, but maybe it's acceptable. You're going to want to decide that. It seems reasonable to think about. What other things might you want to specify here in a specification? Yes, Jason.
One thing I'm concerned about is the return value. So
Yes.
find the index. So
Yeah.
I'm assuming an integer. But
Yeah.
if it's not found, are you going to return a false Boolean? Are you going to return like what value?
You would need to decide on something to return, and I agree with you that there's not a canonical value. Yeah, that's true. This is as specified there in the C language family. Normally that's a signed int, but -1 is pretty unsatisfying because it's not canonical. It's not like the only sensible choice, right? You could say maybe it's min int, the minimum possible value an int could have or something, right? Depending on how you say the first index of str find in, like what index it's in. If that's 1, maybe then it's 0. That's like cannot be found. So it's a little bit troubling there, and I agree with you that you might want to be careful about saying that it returns an int here. It'll be better if you could use some sort of monadic way of saying like it's an option of int, right? It could. I don't know if you've seen these before, but they wrap up an int. It's kind of like an elaborated int that says, is it present or not? And not present would mean it couldn't find it at all. Present, well, the int tells you where it's located. But you'd also want to specify what is the first element of str find in, right? Is that index 0? Is that what it is, or index 1? It's ambiguous, right? Find the index. It's very blunt. You need to unpack this. And thinking about abstractions forces us to go over this in our head. Who could that information that we're talking about be useful for to go over in their head? People testing it, people reviewing it, people mocking it, people using it. And one of the things that is a really healthy thing that thinking through specifications force you to do is to make explicit these assumptions. And it may mean making somewhat arbitrary choices, like is the first index 0 or 1, treated as 0 or 1. You know, with the start of str find in be called index 1. I find str being found at index 1. That means it's found at the very beginning, or do I call it index 0? That's somewhat arbitrary, although you want to make it consistent with use throughout your system. There's some other choices that seem forced almost logically. This is non-null, and it seems like a reasonable thing to come down on either side of this. Yes, Rob.
I guess the other, I think, I don't know if it's been said yet, but it could also be like, did it find it yes or no, 0 or 1, as like, you know, returning value state in actual 17, but did it find it at all? Is it true or false?
Right. Here it says, I mean, I deliberately put down a sort of vague one here, to get us to talk about how can we sharpen it. And, you know, how can we write a specification that is clear and that clues us in. Index suggests it's finding, it's not just 0 or, you know, true or false, but it, you know, that if I didn't say index returns,
find string, string stir find in within this, or sorry, this one within that, then it might be ambiguous, like, are we finding it in the sense of where it is or that it is? But there's another thing here in a lot of languages. Does anyone else want to say this is a kind of basic thing? Yes, Alex.
So one thing, maybe to specify
Uh-huh.
is if it's a 32-bit int, should we specify that the
Mm.
string should be less than 2.1 gigabytes?
That's interesting. Yes. Yeah, good point. Good point.
Good point. Age of big data. Yeah. So fair enough. That actually would be a natural one. And in a lot of typed languages, not all, there's a type-based discipline of how you handle a lack of a reference safely other than null. Null is a very crude way of handling a lack of a reference. We have ways to encode it in our type system that says, for example, whether it's guaranteed to be a reference or whether it could be not a reference, whether it's kind of an option of a reference, or a maybe of a reference. We can distinguish these things. And so some languages don't allow null. In fact, when I was a young man, and we were a lot closer to the fall of the Roman Empire, someone said that the Roman Empire, there's a joke that circulated among software engineers at Microsoft that said the Roman Empire fell because of a null pointer. I always thought that was funny. Anyway, the point is, like, we might want to say whether these, if this is a language where null is automatically allowed for any reference, you could create a null reference. Is that allowed to be passed in? Could you pass in a stir find in that's null? It wouldn't seem to make sense, right? And so you might rule that out as a precondition that these two are not null. Do not call me. You're not allowed to call me with, it's like, you rule out those conditions when people use this function. Do you get that sense? Okay, so something like this finds the first location within this, but here we actually specify the index at the start of stir find in is 0, right? The precondition is this is not null and this is not null, and this one is required to be of length greater than 0, right? Returns the minimum index, that's the first, right? Such that that index such that the substring given by this that it's first place where the stir being found is encountered within stir find, and that's poorly phrased. And -1 if it's not found anywhere. The minimum index, and notice we actually say in this, we actually we refer to another method, extract substring. So we're finding the minimum index I such that extract substring on that index will yield us stir being found. And otherwise -1 if there is no such index. So this is an attempt to provide a thoughtful specification. It pins down a lot of particulars, and you almost can write the assertions coming out, right? Right, want to assert stir find in is not null, stir being found is not null, stir being found length is greater than 0. And then if those are guaranteed, you want to make sure that the range of the value returned at the least is between no less than -1 and otherwise is 0 and 1. Right? Yeah. Ali? Yes.
Isn't it repetitive that the string being found multiple known of that string being found then greater than 0?
String being found, no, it's not ambiguous. Null is very different than the length. This is actually good question, but you need to understand it's very different. In C and C++ and Java, those are two very different things. Having a reference to a string, I'll imagine I have a reference in a variable called V to a string that's empty. It has 0. And this is a string. It's actually a string. It's actually allocated memory.
It just happens to be empty. Versus, I'll call it W, which does not have a reference to anything. It is a null value. I'll write it as like going to ground. Sometimes write it. It's like it contains no reference to any particular string. These are in many languages, I would argue in most languages, these are very different. In some languages, it tries to treat them as being the same, but that way lies madness. and it's really problematic. It's like languages that convert automatically from the string, quote, 8 to the integer 8. That can drive you batty. Yes, Connor.
So would it make sense to write all this
Mhm.
in an interface file, or would it make more sense to write this in like a document file instead? Because I feel like you're writing all this stuff for all your code, it's gonna get really like, I don't know, a bit messy and it's a lot, you know?
You certainly want it for pieces of the code that are widely used outside your module. Like if you have a module, let's say a class, and there's maybe many methods that are used within that class, that those might be lower priority than those that are used throughout the system, where you really do want people to know these things. Now, I will say though, software as a discipline is going in the direction of providing clearer, more crisp ways of encoding information. And if time allows, and I'm not sure it will, but you could find it in slides here. There are formal languages that have come about to exactly prove things. And that's why, like, some people may know the Linux kernel, for example, the correctness of it has been proven by COQ, COQ, this theorem prover system. And people do theorem provers with mission critical software to demonstrate correctness, and they require some clear specification of what this does mathematically. And so software is going in that direction of encouraging specifications for things. Okay, I want to talk a little bit more about, then I want to give you an exercise. Okay, so what I want to see in the context of your code is I want to see for methods, or at least widely used methods, preconditions and postconditions. I will be looking for this every deliverable, and I expect to see specifications. I'm not going to say everything has to be specified for reasons Connor said, but I want to see good use of them and prominent use of them for elements of interfaces that are used across your system, etc. And so they should have preconditions and postconditions. Now, for classes, in ways we're not going to talk about in this session, we're going to have to defer it because of time to another session. You'll also be specifying invariants of that class, things that are at any one time true, in history properties, things that, if you consider how it evolves over time, if it's a mutable class, properties that are guaranteed as it evolves. For example, that it can only stay the same or increase in value for a certain attribute or field. Now, there's multiple ways of making specifications. Probably the most common one is preconditions and postconditions. There are times we sometimes describe what are called effects. So I'm going to show two different types of specifications. We're going to see a couple examples, and then I want to give you these exercises. So some specifications are quite operational, like this one here. Search, okay, we're searching for an integer in this array, right? And here we're using exceptions to signal we can't find it, or that we passed in something that's null. And so if it's null, we throw that. Otherwise, it goes one by one. Notice it even says the order. It's describing how we search for it. It returns the index of the first one in the tab. And if none of them do, we throw this exception. That would be enough. Exceptions are very heavyweight things. We may talk about this later in the class, depending on needs. But generally exceptions are very computationally expensive. And we want to be careful. But if you're dealing with very large arrays, where searching for it may take a long time and it may not hurt you that much, particularly if this is a matter of error handling. It shouldn't happen much. It should happen only in error circumstances. Throwing not found exception may be acceptable. A declarative, so this operational specification focuses on how it accomplishes it. Search one by one in order, from the beginning of A onwards. A declarative or definitional specification will say, it returns the I such that this A of I equals X, and it will signal this if there's no such I. It doesn't say in what order it searches for it, nor does it make a guarantee as to, well, what guarantee does this top one provide, this bottom one doesn't? What is guarantee? Like, what thing can I count on in this top one if the bottom one doesn't? Yes, Connor.
Then it searches in an order.
In order. And so the first one, this specification implies and restricts the implementer of search to have to return the first. And that may be onerous or it may not be, depending on the data structure that by which they undertake this search. Or in the algorithm through which they take this search. But this later one, it gives flexibility. It doesn't provide any guarantee as to whether it's the first, just says if there is one, it will return that, otherwise string not found. And in general, the declarative approach, the approach that says what it does, not how, is easier to understand. It has more flexibility. It's greater potential for automated reasoning. But an operational approach, gives some significant information. Okay, we talked about the first of these. Your job with these is to come up with some thoughtful ways of sharpening that, recognizing there's a lot of latitude here. So the second one, we talked about the first. The second one is going to be counting the number of occurrences of string being found within string finding. You're gonna count the number of occurrences. I'm providing a weekly sort of description that's for you to sharpen up. Extract substring, we'll grab the substring within string that starts at index start and ends at index final. It'll give us the string back. It's the idea. And I want you to work with, you can work by yourself or with up to 3 people. Put your names in the top to try to create specification. We will go for about 10 minutes on this, and we will then collect them and talk about them a little bit. Okay, so the problem is I don't know how many people are going to work in groups. So okay, so one for you 3. Okay, up to 3 people. So okay, 2 and 2. Yeah, great. Let me. We got like a row-based collaboration environment. Okay, so you do
I feel like for the
it will be for grades.
again, we don't.
So, but what I'm going to be looking for is thoughtfulness with it. I'm not judging completeness. I'm checking if we gave it a serious try. Part of my goal here is to incentivize people to less. So I'm going to be very liberally. I'm not going to say like you forgot this condition. So be sure to put down your names, all of your names on this. Does anyone want one more? Anyone need another?
Return value, like, and, or you can, unless you just submit 1K.
Yeah, just,
So what is your? Oh, no, return start off, yeah. The length,
The length for this.
the length is bigger.
Yeah. That's great.
And then publish and find it in. Yeah, being there. Yeah, that could be like.
We also need to write like the.
Yeah.
We could throw an exception. I just need to decide for if no substrate is found. They want to throw it, that's what you want. So, for here.
I'd say it's functions.
The only thing that is here, you wouldn't, it's accounting for, so the zero occurrences.
Yeah, I guess.
But that would make sense. Yeah. Yeah. Yeah, there's no.
Like, we have included like the baby found being ordered than like those being. Less than like what you or like spring find in being. Lands on stars like I in
Is that?
Yeah.
Just saying, you know, that is one of the things that. Or like we can have like.
Yeah, contribute not for
Oh, you're right. I saw so stressful. I was leaving.
And it was good for the first year.
Yeah.
Yeah, that's a baby.
Oh, yeah, that's right. Maybe there's any.
Yeah, that's right.
It's like as long as if they're middle, you know, that would be exceptions, but like. That's it. Final.
It gives us the thing from starting to final.
Yeah, we put a string in, you give us from start to final.
Null and final. Like start and final can't be. Start with zero.
Oh, you're starting. Start can't be greater than the length string.
Oh, no.
So I think really, yeah, starting and final. One thing that's making sure everything here.
That could be an exception.
We're really saying that we're kind of single.
Oh, yeah. That's what, final can't be less than start.
Yeah. Yeah.
So it's even care where they are.
Yeah.
That's correct. Oh, there's only that.
Yeah.
Wow.
The first one is doing code. Yeah. Can be left start and then start. But yeah, we vice versa. Yeah.
Okay, we're gonna go for another three or so minutes here, 3 to 4 minutes.
We got here. Okay, what's like a black hole? I was like, what does it say? No, fair enough. Randy starts to not be accurate. One more I was thinking of. We can take start on second grade 0.
Okay, oh no, we said if it was 0. it was
Yeah. -1.
Oh.
Right. Yeah, yeah. Yeah.
Well, the thing is, so you're talking about just start from here. So it doesn't matter if it's automatic or no, you can always do that. You gotta turn from 0 to 8.
Yeah.
So okay, you can write that as a higher level of thing, like that. That's what you call it. And also, what is the string? Like, what is the string?
But again, yeah.
Another minute or two here.
I think that's good.
Well, the posting is right.
Yeah. I feel it's always focused to that side.
Sometimes.
Started at 1. Like.
I've been working about like a year. What? Really? I mean, I swear, I teach kids how to do that. Oh, you know what? That's probably. It is right. The kids in my work think, oh, what's kids?
Yeah.
Where do you work? Okay. I just know like figures what they like.
A lot of the goal is to make sure that students are coming and engaging with their groups and so on in class. So I'll unmute here. We're going to be going over, and I know you folks have to get back. Maybe I'll first comment on the which of those was harder, this first or the second? Which is more interesting?
The second one's more interesting now.
Interesting.
The first one's harder. Yeah. First one's less like.
Second interesting. Which one is harder?
The first one.
Okay. I would agree with both those assessments. For me, it's the same. But I think as a general point, so I'll give you these slides, give you some thought, but I think most of you got some of the issues. You've got for the second one, these kind of mutual constraints between the string and its length and the logical relationship of start and final to that string. Like start can't be less than 0, right? And final can't suggest an index greater than the length than the string would allow. But at the same time, start and final have a relationship to each other. Like you can't have final be less than start, and both have to be 0 or more. You know, if we define index 0, and it's very important that we be clear what's the first index of strings, 1 or 0, right? So all of these things play a role here, and I hope it's sinking in that like this forces you to think through what are the logical things needed for the conditions to be logically coherent, to be consistent with each other. And that is a good exercise to go through if you're going to write this.
you're gonna test it, if you're gonna mock it, if you're gonna review it, and it engages you. And I'm not saying you have to do this for every routine, but it's really good if you do it with routines that are gonna play a bigger role in your system and gonna be widely used. Now, the second, this first one is the one I gave you, right? The sure being found and sure find in here. You've got a need to like break it down. Okay, we're gonna return the count of distinct indices. They've got to be distinct. We're not gonna count something as multiple times for one, but we've got to count the number of distinct ones in which the substrate given by this is found within sure find in. And that may allow for, this is important, how you specify this may allow to consider overlapping instances to be different strings, right? If I'm looking, if I have an empty string, you know, if I have forgive me, this is A B, and I'm looking for, you know, A B, sorry, right, like, okay, this may be a first, but then here's a second, and they overlap. Is that distinct? Is that not allowed? Does like the first one say, okay, you have to start looking after that? Generally, we wouldn't think that way, but how you define this might imply accidentally whether you allow for overlapping ones, right? Now, once you go through this exercise, it starts leading you to start to think about test cases too. And we're going to be seeing that. Like it invites testing of certain sorts to see, does it handle this? Does it handle that condition? And it almost again rolls off the list of conditions which you offer. Because often you want to see, does something work if it's being used properly, and how does something react? Does it react gracefully if it's not being used properly? And that's one philosophy of building software, make it able to handle cases where it's not being used properly, and it should signal that, like with an exception or something. But alternatively, at the very least, you want to assert that these preconditions are not met. I don't have the information I need to do my job. Go back and fix their code, you know, whoever's using it. So I'll give you, you know, some of these examples, but we're over time. I would like to see you use the same focus you used here in your projects, okay? Thank you, everyone. And have a good break.